All right, we're going to get started pretty shortly. So today is going to be our last lecture of the year. You have a question? Yeah. I just started. So, as I said, today is going to be our last ML lecture. So we're going to be talking about transformers. So make sure if you guys haven't signed in to sign in. And then at the end of the lecture, we're going to announce also the winners for our Base 44 hackathon. So make sure you guys stay until the end for that if you're looking for that. So introductions. My name is Alvin Wong. I'm the education lead of GatorAI. And the other ML lecturers who help me sometimes with the lectures are Kartik, Siobhan, and Srinikath. All right, so let's get right into it. So transformers, so what is a transformer? So it's a deep learning model introduced in Attention is All You Need, which is a research paper by Vaswani et al. For modeling sequences, right, where the tokens in the sequence kind of depend on each other, and it's using a mechanic called attention, right, which is right in the title of the paper. And so the motivation beyond this kind of new type of deep learning model is because traditional sequence models like recurrent neural networks are they're non-parallelizable, which means you can't make them very efficient because they have to go through back and forth. And they also struggled with long-term dependencies. And just as a reminder of a recurrent neural network it's a neural network where each neuron basically has some sort of memory, right, which is just some number that it basically uses in its weight and bias calculation, and it just basically adds it to itself, right? And we can see here how there's an arrow from neuron 1 back to itself, and also that neuron 1 is connected to all of the neurons in the previous layer, and it's also connected to all of the neurons in the output layer. So yeah, if there's any questions also, just feel free to raise your hand and ask away. All right. So now that we know what transformers are, right, which is a type of deep learning model, let's talk about the key idea behind them, which is this mechanic called attention, right? So transformers removes the reliance in recurrence entirely, right? And it uses only attention, right? And so you can think of a transformer as composed of two separate layers, which is an autoencoder part and really a decoder part. And sometimes it's just one, and we'll talk about how transformers can be either just an autoencoder or just a decoder, or can be both, right? All right, so let's define what attention actually is here. So attention, right, is the key mechanic used in transformers, and it's used essentially to compute how much each token in a sequence, right, or in most cases words, right, in a sentence should matter to another word in the sentence, right, using something called queries, keys, and values, right? And so this enables direct connections between tokens in a sequence. And we can kind of see an example, right, of how attention is kind of looked at. It's looked at as a matrix, right? And we can see here we have a sentence, the cat sat on the mat, right? And so essentially what we're looking at in the attention matrix is how much does each word or each token in the sequence matter to another word in the sentence, right? And it is direction dependent, right? So for example, the corresponds to the, right? It's going from the to the, and then the going to cat, right, has a 0 attention score, but cat going to the, or the going to cat, right, is different, right? And we can see here, the going to cat and cat going to the are two different. They both have zeros here, but the direction of the tokens matters, right, in the attention. And so we can kind of see how that works here. All right, so let's talk about the encoder part of the transformer, which is the first kind of layer that is normally used in a transformer. And some of you guys might be familiar with this graphic that was in the paper, right? And that is kind of a graphic of depicting the model of a transformer, right? So the encoder uses, right, attention, and it uses feed-forward neural network layers to essentially do its calculations. The input to an encoder is basically any kind of sequence, right? So you can think of this as a sentence. Another type of sequence, right, is used. And the output is essentially just the sequence given back to you, but it's enriched with contextual representation of the entire sequence. And some examples of an encoder-only architecture are something like BERT, which is bidirectional encoder, and basically it's just used for getting a representation, an enriched representation of the sequence. So let's go through exactly what an encoder does, right? So let's say that we have a sequence of text, right? And for now, we're going to say that each token is a word. So we have something like we have text that starts with the dog chased, and we have more words, and then it ends with the word city, right? So what we can do to these words is, because we can't input words directly into a neural network or any kind of like machine learning model, what we have to do is we have to turn them into what we call vectors, right? And so we can see here that we turn the words into vectors, right? Such that every single row in this X matrix is essentially a vector representation of that word. So x1, x12, onwards to x1d is essentially all of those numbers together represents the word the, right? And same for the second row. The second row, x21, x22, all the way to x2d, all of those numbers form a vector, and that vector represents the word dog, right? And we can see exactly where we are in the autoencoder architecture. So the autoencoder architecture is just this left part here, and right now we're on here, right? Where we take essentially the inputs and we do something called input embedding to convert them into vectors. And the positional encoding is just something you add on top of that to add the positions of the tokens, but for now we'll skip that because it's not super important. So let's say we have now all of our vectors, right? And we have our text or a sequence represented in this matrix that is denoted as X, right? So what happens? So now we're going to send it to the mechanic of attention, right? So essentially what we do is we take our text, which is now represented as vectors, right? And it's an element of the reals, right, to the length of the text times the hidden dimension, which is how many numbers we're using to represent a single word, right? And essentially what we do is we calculate these three separate matrices, right? The key, query, and value matrices using X, right? And essentially we calculate it using matrix multiplication with WQ, WK, and WV, which they correspond to the weights relative to those key query values, right? So we can see here that they're learned weight matrices, and we essentially just multiply them with our text, right? And this essentially gives us three matrices that we can now use in our calculation. And so essentially what we do is we take these key query value matrices and we calculate a new matrix called attention, right? Which is A here. And what it really represents is how much each token attends to another token, right? So to kind of think a bit about it conceptually, the first row in Q is basically the first word, right, in that text, and it's basically asking what other tokens should I be, looking for, right, or what tokens should I be willing to give my information to, right? And so Q1 is, how much the token attend to itself, and so on. The keys is, what kind of information should I take in, right? So K11 is what kind of information should I take in as from a token to myself, right? K12 is, what kind of information or how much information should I take in from the second token, and so on, right? And so we can think of that conceptually here. And then the value matrix is what information is being passed in, right? So the key and query matrices represents kind of the gate, so how much information should be passed to the tokens from token to token, right, depending on the direction. And then the value matrix is what kind of information should be passed to that token if the token actually attends to each other, right? And so essentially what we do is we do the matrix multiplication of the key and queries, right? Because those multiplied together give us all of the attention tokens or the attention values of every single token, right? And then we obviously had to transpose it to get the right matrix multiplication. And then we divide it by a constant decay, which is meant to just eventually scale down all of the values in these matrices, or they can kind of get too big, right, for computers to handle, so we want to scale them down. And essentially, we just take a softmax, right, of every value in the matrix. And so essentially, A is just a matrix, right, where every single value just represents how one token attends to another, or how one token should attend to another. And then we multiply that with V, right, which is the value, and that determines what kind of information gets passed through, right? And so what we get is that Z is a matrix with the same dimensions as X, right? But it just really represents the new context-aware representations of X, right? And we see this is all still within the self-attention parts, right, of the encoder. So Z represents the new context-aware representation of X. And essentially all we do is we pass Z, right, into our feed-forward neural network, right? And essentially what we do is we kind of learn some relationships in between the tokens that are now kind of enriched with that information, right? And we essentially get E, which is our encoder output, right? And it's just a matrix, right? And we can see here that is the exact same dimension, right, as our original text, right? It's the exact same dimension. It's just that we've now enriched it with the context between itself and other tokens, right? And we pass it through this neural network. Now, normally, encoder-only models are used for something like text classification, right? So how you would do that is normally what you would have is a special token, right, or a special first vector that kind of gathers all the information, and then you would pass that into another neural network to kind of train as a text classifier. And eventually you train the neural network and the attention block together. And essentially what happens is as you train it together, the transformer is able to learn to kind of give all of the correct information to that first token to pass it to the neural network to then classify your text. All right. Does anyone have any questions? I know it's a bit dense. All right, we'll keep going. All right. So let's take a step back from all of the math, right? So what an encoder actually is, right? Let's do a recap. It uses stacked self-attention and feed-forward layers. So it'll do that attention thing a bunch of times on top of each other, right? And so then we'll get an output, right? And essentially the input is any sequence, right, that we want, right, like a sentence. And essentially the output of the encoder is a contextual representation of the entire sequence, right? Where we just get a matrix where every single row in that matrix represents a word, but the word is enriched, right, with the context from the other words in the sentence, right, if that makes sense, or the text. All right, so let's look at the decoder part, and we have a question.
Yeah, quick question. When you say enriched, what does that look like? Is it like the multiplication happens and it's a new number, or is it like what do you mean by enriched?
Yeah, so basically, right, we start, right, with our text, right, and it gets embedded into vector representation, right? And when I mean enriched, I mean it literally goes through all those matrix multiplications, and the numbers themselves for that row will change, right? But the transformer will have like an internal kind of mapping of what the vectors mean. So it's able to essentially learn an internal mapping, and it'll change the vectors in that row or of that word, right, to essentially be what it wants to be, right? And that's essentially how it happens. But that's a good question. All right, so we'll go on to decoders now. So decoders generate output tokens using mass self-attention, and they also use something called cross-attention, which we might skip depending on the time. And some examples of decoder-only models are generative models, so they just generate text, and we'll see exactly how a decoder-only model can generate text rather than kind of represent all of the information. So let's go through some of this stuff that we went through before, right? So let's say we have some text, right? The dog chased the. What the decoder will do is it will predict the next word in the sequence, right? And this is probably very similar to how you guys have heard that ChatGPT or other LLMs work, right? They take the sentence or the prompt that you give it, and they basically just predict the next token in the sequence, and they just keep doing that over and over again, right? So let's see here. We have the dog chased the. So it's going to get embedded right here, and it's going to be represented as a matrix, right, where every single row represents one word, right? We're going to do our attention calculations again this time, but we're going to do them a little bit differently. How instead we're going to do the attention is we're going to add essentially what is called a mask, and that's why it's obviously called masked, attention, right? Or essentially what we do is we take our matrices and we multiply it by this masking matrix. And essentially what it does is it prevents tokens looking at future tokens to give it contextual information, right? So we can think about this here, right, where the first word essentially can only look at itself, right, because it's adding 0, so it's adding nothing. But if it's negative infinity, it'll just change anything after it to negative infinity, right? So the information from the tokens in front of it is basically like demolished, right? You can't get any information from that. So same for the second word. The second word can look at the first word, right? And it can also look at the second word, which is itself, but it can't look at the third or the fourth word in our sentence, right? Which is the dog chased the, right? And so on and so forth. And so we will add this mask so that way the tokens can only attend to previous tokens here. And essentially what we'll do is we'll compute our attention matrix and then we'll multiply it against the value matrix, right? And then essentially what we'll do is we'll pass it into a neural network, right? And the neural network will then take all of this information and it will try to predict the next value, right? Or the next token in the sequence by essentially only taking the top vector, or the latest token, right? The latest token vector representation, right? And I'll essentially pass it through a neural network to kind of predict the next token, right, in the sequence. And we can see that here. So a decoder-only model will skip kind of this connection with the encoder, and it'll only have its own masked attention, and then it'll have its feed-forward, and then its final neural network to calculate the probabilities, right, for the next token in the sequence. All right, so now we're going to look at the encoder-decoder models, which are the models put together, right? So the decoder uses masked self-attention and the output of the encoder to kind of feed back into itself. Normally, it was originally used for machine translation, and essentially how that would work is that the autoencoder was used to represent like the original root language. So let's say you're translating from English to French. You would give the English sentence to the autoencoder, and then the decoder, you would give it kind of like an empty sentence almost, and essentially the decoder would take the representation from the autoencoder and try to predict the next word but in French, right? And so that's kind of how this kind of architecture came to be. But then people started playing around with it, and they realized that encoder-only models are kind of good and decoder-only models are kind of good. But encoder-decoder was kind of what this was created for. So in encoder-decoder, it's the same thing, right? We will get the key, query, and value matrices, right? And we'll calculate them through these learned matrices, right? And we will calculate our attention as normally, right? But what we do is we calculate the queries using Z, right, which is the current representation from the output, and then we'll use E for our keys, and E comes from the autoencoder here, right? So essentially what we're doing is we're basically taking the decoder output and we're looking what tokens in the original root sentence do I need to look at for me to get the correct information, right? And so it's basically just passing the information from the autoencoder representation to the decoder, right? It's very, very simple in that sense. And then essentially we just do the same thing. We multiply our new attention matrix with the value matrix, right? And then essentially all we do is pass it through our feed-forward neural network and then do our final linear and softmax layer, and that will predict the next token in the sequence based on the information from the autoencoder and also the information from the current and previous tokens in the decoder sequence. All right. Any questions so far? No? All right. That was a bit dense. So we are going to go quickly into a demo here. So if everybody could go to colab.research.google.com, we'll get started, and then after that, we'll announce the base 44 winners. So we're just going to be here on our Colab, or an empty Colab, and we're going to code together. So what we're going to code is a decoder-only model. So it's meant to, right, generate text. And that's all it's meant to do, right, using the tokens from the previous. So let's first start with installing all of the libraries that we need to use. And so we can do this in Colab here because this is how you get them in Colab. So you can get libraries that are not a part of the standard runtime for Colab. And then we'll import the other ones. So data sets. Config. All right, and just make sure you're running all of your cells as you go through, right? So we're just gonna train it on very simple text. We're gonna train it on this sentence, but repeated like 1,000 times. And essentially what we hope to do is we hope that eventually after being trained enough, it can essentially just generate, right, the correct code. So we're just essentially going to have this string and have it be 100 times the length, right? It's just going to be this string repeated 100 times. And so what we need is we need the vocab, right, of our text. And we also need to represent our words, right, as indices, right? So we're going to get the string to the index. All right. And then we're also going to get the other way back, which is string to indice to string, right? And then we're going to get the IDs. And what we're doing here is we're having each character be a token. Normally, how you tokenize your sequence of words depends on what strategy you want to do. But to make this easier for us, we're just going to have the characters be the individual tokens. So we'll run that and we get it to work. Next, we're going to define our block size. And we're going to get examples, right, or demonstrations that we want to feed into our transformer. So essentially what we're doing here is we are creating a set or a list essentially of strings that are taken from the very long text that we have created before. Range IDs minus block size. All right. And then we will create a data set from this set of examples. Make sure you run that and it works. All right. And now we are going to define a helper function, which is the collate function. And this essentially is just taking a batch of examples, right, and tells us how to stack them against each other. And this is needed because the sequences might not be the same size. For us, that is the case, but it's normally good practice, so we'll have it. Input IDs for B in batch. D-type equals torch.long. And now we'll just return input IDs X, and the labels will also be, will just be x.clone. Right, and the reason we want this to have the input IDs be X and the x.clone for the labels is because we just want it to essentially recreate the text, right, as faithfully as it can. All right, so now let's define the parameters for our transformer model. So we're going to use the transformer library that we used before to make it easier for us, so we don't need to kind of build everything entirely from scratch. But essentially, we're going to do this and set the hyperparameters for our thing. And positions equals block size, ctx also equals block size. The number of embeddings will be 64, and layers is 2, and end head equals 2 as well. All right. Make sure it runs. Oh, forgot something. And we'll initialize our model using this. All right. Now we're going to set the arguments for our training. If I'm going too fast, just let me know and I can slow down. Also zoom in a bit for you guys. Per device train. Now we are going to define our trainer to actually train our model. So model equals model, args equals args. Syntax. Train data set equals data set train, right? From the data set that we had previously created. Oops. Train data set. Test, or eval, I mean. Test, right? And our data collator is the collate helper function that we defined before. Additional argument line follows keyword args equals args. Train data set equals ds test. All right, there we go. So now that we've defined our trainer, we can finally train our model on our data set, right? Which is just the same sentence repeated, or the same 3 sentences, I mean, repeated 100 times. And I recommend that you, trainer indice logits, too many indices for tensor of dimension 2. So we've ran into an issue. So let's go back and make sure we check everything. No, sorry, SCI for numerator. Unfortunate. Size equals train dot here. Sorry. All right, so we're missing this. IDs I for I in range, length IDs minus block size should be good here. All right, so we'll rerun this, and then if we rerun this, will it break? Of course. It'd be too easy to have everything work. All right, so you have to rerun some of your cells to kind of change the data set and stuff like that. But just rerun all the cells after that, and we'll be able to see our model training. So we can see that the training loss and the validation loss is decreasing, right, which is a good thing. And after that, we'll be able to kind of test our model and see how well it is, how good it is at predicting the next token in a sequence if we give it some, kind of prompt or something like that. So after 5 epochs, our training loss decreased and our validation loss decreased as well, not by a lot, but let's see how it fares, right, to the test, right? So let's make our prompt, right? So we want the dog chase the, right? And we want it to hopefully say ball, right? And essentially what we want to do is we're going to have this prompt be the starter for our decoder model, right? All right, so we're going to, if you are using a GPU on Colab, you will not need this line. So you can check if you're using a GPU or not by clicking this arrow here and doing change runtime. If you're on CPU, you don't need the line. I think the line will actually break your demonstration. If you're on GPU like me, you want to have that line. So I'm on the GPU, so that's why I'm going to have that line. All right. And we're going to have our attention mask, right? And essentially what we're going to do is we're going to get the output from our model, and we're going to pass in the input IDs. We're going to pass in our attention mask. And we are going to define how many tokens we want, right? And since we want it to be ball, hopefully, we're going to say 4 tokens, right? Because that's how many characters are in the word ball. So we're going to do that. And then we're going to pad token model.config token ID. Right. All right. Name input IDs is not defined. Let's see here. Can you not define input IDs? So IDs? Maybe IDs. This object has no attribute to IDs. Interesting. I think we ran into another bug. IDs equals input IDs. Input IDs. Let me see. Wait, let me double check this. Dog started IDs. I think it's this for C and prompt. I think this is right. If I'm mistaken, I will be very sad. This object has no input IDs. Why is stoy also not? For Steve IDs. Interesting. Let me double check this real quickly. Sorry for the mishap. Let me see this. All right. I might have changed something. Let me check the history. Revision history. Going to check here. IDs, input IDs. Oh, that's really right now. Well, that's too early. So right here. Tokenized or no? That's 2. Cross source. Data sets, import data sets. Oh, wait, this is the other one. Sorry, give me a moment. Okay. Regardless, essentially what you should get is you should be able to print out, and you should essentially be able to show that the transformer model would output ball. Essentially is what would happen. Essentially that's it for the demonstration. I think I can figure out maybe what went wrong if take a look at this. Input IDs. Okay. We need to do a torch.tensor here. All right. Please tell me this now works. Name inputs IDs. This object has no attribute shape. Okay, we've got to define the deep type. I guess not. Input IDs equals source tensor C for C and prom. That's right. Tensor. All right. I think I've messed up the code a little bit, but anyways, that's about it. So thank you guys so much for coming today. And now we are going to present the Base 44 hackathon winners. So I'm going to stop the streaming now. But thank you.